So in this class, we have now talked about the nucleus, which consists of protons and neutrons. Okay. And then we talked briefly about Bohr's model of the electron, saying that Bohr anticipated that what electrons did was they actually rotated around the nucleus. And that's kind of the traditional Jimmy Neutron-esque vision of an atom that we've had. And now I'm going to crush your worlds, unfortunately, and explain that, in fact, this Bohr model is not correct. Electrons do not rotate around the nucleus, and instead they exist in what are called orbitals. Now, orbitals are regions where electrons are most likely going to be found. So one such region is the s orbital. So notice the s orbital here is a sphere, okay? And so electrons within this s orbital, so if we designate electrons to this orbital, which I'll show you what that means in a second, what we're saying is there's a high chance that we'll find it within this region, okay? If you notice the next regions, there are 3 of them. So there's the 2px, so it goes along the x-axis like this. So this region, this is one orbital. So this is one region where you will likely find electrons. Another region where you will likely find electrons is the 2py right there. So this, we call it a dumbbell shape. And then along the z-axis. So there are 3 different orbitals here. And it looks, when you put them all together, these are the regions where you will likely find the electrons that we designate to that orbital. Now, notice I've been using the term orbital, but then in your notes it says sublevel. So the s sublevel has just one orbital, this one shape. The p sublevel has 3 orbitals, these 3 different shapes. Okay? If we go down to the d orbitals, we've got 5 different regions where electrons are likely to be found, okay? And notice they're very unique looking shapes, but they're 5 different orbitals, 5 different shapes. And so the d sublevel has 5 orbitals. And then we even get to F, but we're not going to draw it because it's just too crazy. But there are 7 different configurations for the F sublevel. Okay? So before I make sense of these shapes and actually show you where the electrons exactly are going. And remember, it's not this idyllic rotation of an electron around a nucleus. In fact, it's simply electrons moving around randomly, but we can predict or say with a certain amount of certainty, we think there's a likely chance it will be within either the s orbital, one of these 3p orbitals, or one of these 5d orbitals at a given time. It doesn't guarantee anything, but that's where they're most likely going to be found. And the reason why that's important is because that helps us to be able to predict how atoms are going to react together. Okay? So before I actually show you what this looks like with atoms and their electrons, I need to discuss electron configurations. First of all, each of these rows represents an energy level. So this is my first energy level, so we're going to call it n equals 1. This is n equals 2, n equals 3, and so forth. Okay. Next, the regions. Okay. So the first region that I'm going to show you is for the s orbitals. So I'm going to highlight this region here. Okay, and then helium, because helium's always a little bit strange. Okay, so that is the S for the s orbital. So here's how I'm going to write the electron configuration. I'm going to first put the principal energy level, which is 1 for this first row. Then I'm going to put the orbital, so this is going to be s. And I only have 1 electron so far, so I'm going to just put a 1 up top. Okay, so the 1 superscript represents the number of electrons. Okay, I'm going to move over to helium. I'm in the first energy level still. I'm in S, and I now have 2 electrons. Okay, now I'm going to go down here. Now I'm in the second energy level. I'm in S, and I have only 1 electron because I've started a new principal energy level. Okay, same thing here, 2 S, but now I have 2 electrons. So you can start to see a pattern. Now I'm in 3S, so I've got 1 new electron. So you guys can fill this in. Okay, now I'm going to do that, but for my P sublevel. So for the P sublevel, it's this region right here. And just like with the S sublevel, okay, notice this is I have my first energy level in the first row. So P actually starts in the second energy level. So it's going to be 2 because I'm in the second energy level. I'm now in the P sublevel, and I've just added my first electron to that sublevel. Okay, the next one's going to be 2p2, then 2p3, then 2p4, 2p5, and 2p6. Okay, so notice for S, this S sublevel, you can fit only 2 electrons total. For the P sublevel, you can fit a total of 6. So I'm going to go to the next energy level, which is 3. So it's going to be 3p, and I start all over again. So it's going to be 3p1, then 3p2. Okay. You get the point. So I'm going to just write these out quickly. Okay, now I'm going to do this D sublevel. And the one quirky thing that you'll notice for the periodic table is that I'm missing the 2 elements in the 6th and 7th energy level. Those are actually just right here. We moved them down, and the reason why these 2 rows were moved down is simply to make space, right? Because otherwise the periodic table would be a lot longer than it is. All right, so there's only one weird thing about the D sublevel. So for the D sublevel, you would expect it to start at 4D1 since we're in the 4th energy level. But just based on the rules as far as energy is concerned for the electrons, which we'll discuss in a future lesson, it actually starts in the 3rd. So instead of being 4D, it's 3D. So it's 3D1, 3D2, and then we just keep going. The D orbital for this 5th energy level will actually start right here, so 5D1, because it's supposed to be right here actually. Okay, and then I'm going to keep going. And then the final sublevel is the F sublevel, which is this group down here. And just like the D sublevel started one energy level lower, the F sublevel, you would think it would be in accordance with the D sublevel. It would start at 5F, but actually it starts one energy level even lower. So this is going to be 4F1. So notice, unlike the D sublevel, which can fit 10 electrons, the F sublevel can now fit 14. Okay, so this is a lot of numbers and letters, but what exactly does it mean? What can it tell me when I'm trying to write out an electron configuration, and what exactly is an electron configuration? Well, what an electron configuration tells you is where electrons will likely be located. Okay, so let me write out one sample electron configuration to walk you through it, and then we can actually look at what exactly it means. So let's look at the first example, phosphorus. Okay, so we're going to use this sample periodic table here. Obviously, this is not what your periodic table looks like, and it's not what I will give to you on a quiz or a test. You will just be using a regular periodic table. But for right now, we're going to practice using it until you get comfortable using the periodic table to write out the electron configuration. So I ask for the electron configuration of phosphorus. So if you look at the periodic table, phosphorus is going to be located right here. Okay, so to write out the electron configuration, I'm going to read this periodic table like a book. I'm going to start at the beginning, the far left, top left corner, and I'm going to read left to right. Okay, so when I'm reading this, I read 1s1, 1s2. Okay, I'm not going to write out 1s1, 1s2. Instead, what I'm going to do is I'm just going to write 1s2. Okay, so this is going to be 1s2. Okay, I'm going to keep reading. So I've got 1s2, then 2s2, then 2p6, then 3s2, and then 3p3, and that is where I end. Now, the reason why I don't write 2p1, 2p2, 2p3, 2p4, 2p5, 2p6 is once I write 2p6, it's implied by putting 6, saying I have 6 electrons, that I've included every single one of these boxes. Okay, so let me write that down here. So as I noted, the electron configuration would be 1s2, 2s2, 2p6, 3s2, and then 3p3. So what this is telling me, if you look at this, I know I have 2 electrons in this 1s orbital, 2 electrons in this 2s orbital, 6 electrons within these 2p orbitals, 2 electrons in the 3s, and then 3 electrons in the 3p. So let me show you what that looks like. And this is going to be a really crude drawing. Sorry, I'm not a great artist. There's my nucleus. So it's saying these first 2 electrons are most likely going to be found within this spherical region here. So I will have 2 electrons there, just floating around, hanging out. Okay? Then it tells me I will have an additional 2 electrons that can be floating within that entire 2s orbital. So it can go within this, it can go within where the 1s orbital is. It's just simply a bigger area where you will likely find electrons. Okay? For 2p, it is saying within, and see how messy it already is going to get, within these 3 different orbitals, and then there's one coming out of the page at you. Within those 3 orbitals, okay, I will likely find 6 different electrons floating within that region. Somewhere within that region. Then I have 3s. Well, 3s is going to be a sphere as well, but simply larger. So I will have 2 electrons likely within that 3s orbital. And that was 2p. Sorry about that. Okay, so 2 electrons floating somewhere within that entire green region. And then finally for 3p, I'm going to have 3 electrons likely found within that large region. Okay, so just 3 electrons there. Okay, now, this might look like a mess, and it is, because not only does it look messy, but those regions don't guarantee that's where I'm going to find the electron. But it is more accurate than this concept of just an electron rotating around the nucleus. So keep in mind your s orbitals. Okay, for your s sublevel, you've got 1 orbital, you've got that 1 spherical shape. For p, you've got those 3 different orbitals, those 3 different shapes. The principal energy levels, as you guys just saw, tell you basically how large that shape will be. So when I compare 1s with 2s and 3s, the size of the sphere simply is getting larger. For 2p and 3p, the only difference really is the size of the orbitals. Now, the good news for you is for this class and for any chemistry class you take, instead of having to draw out this beast, you just have to write out the electron configuration, which for phosphorus would be 1s2, 2s2, 2p6, 3s2, 3p3. Okay? Knowing what it looks like is valuable, but you're not going to be asked to draw that. Let's look at the next example, manganese. So manganese is right here. So I'm going to read this out. I'm going to read it like a book again. So I'm going to start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d5. So I'm going to write that out now. Okay. I'm not even going to attempt to draw a diagram to show where those electrons are for that one. Okay.
So for this next practice problem, I'm going to have us use a regular periodic table instead of the periodic table that we just created that shows you all the electron configurations.
All right, so I want to find the electron configuration of nickel. Okay, so keep in mind, this is my S sublevel. This is my P sublevel. Remember, helium is S sublevel. This is my D sublevel. Okay, so I'm going to write this out. 1s, 2, and notice I put all the principal energy levels here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3, because remember D starts at 1 energy level lower, 3d, and if you count across, that'll be 8. So this will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. So in a previous lesson, I had actually drawn out all of the orbitals in order to explain electron configurations. So I'm going to quickly do that, and then in this lesson, I'm going to make your life a lot easier by showing you how we can actually simplify that by drawing what are called orbital diagrams. For the first example problem, I'm asking about chlorine. So just as a quick review, the electron configuration for chlorine is 1s2, 2s2, 2p6, 3s2, and then 3p5. Okay? And this is what I had explained. This is what I had drawn out. All right, 1s is going to be spherical in shape. So first of all, I'm going to draw my nucleus. Okay, those 2 electrons that are in the 1s orbital, there is a very high chance they're going to be within this 1s orbital, right? 2 electrons floating around. Not a guarantee they'll be in there, but there's a good chance. Okay? Then there are going to be 2 more electrons in the 2p orbital. They can be floating, and they can even go into the region where the 1s was, right? The 2p includes everything that's within this purple circle. Then for 2p, it gets a little bit messier. Remember, it looks like this. So there are 2 electrons that could be in this orbital. There are 2 more electrons that could be in this orbital. And 2 more that could be in this one that's supposed to be coming out of the page, but I'm not very great at drawing. Okay, so a total of 6 electrons. And remember, these are the regions where you're most likely going to find the electrons. Then I look at 3s, a bigger circle, sphere, sorry, not a circle, sphere. Okay, so this is going to be your 3s. Again, 2 electrons within this region, likely. Okay, and then 3p. Notice the s's, the s orbitals, simply get larger, going from 1s, 2s, 3s. Same thing with p. 2p has the same shape as 3p, except it's just smaller. So 3p is going to be even larger. And notice you can fit a total of 5 electrons for chlorine in this orbital. Now, if you can imagine me asking you every single time you wrote out an electron configuration to also draw this in order to see what's going on with the electrons, your brain would hurt a lot. Okay? So instead, we have an easier way of drawing your orbital diagrams, and here's how we do it. Notice for all s orbitals, for the s sublevel, you only have 1 orbital. You have 1 shape. It's a sphere. And so we represent that with just a box. Okay, so I'm going to space out my electron configuration quickly for chlorine. Give me 1 sec. All right, so because there's only 1 orbital in the s sublevel, I'm going to just represent that orbital with a box. And these electrons that are floating around, in order for them to be stable, the rule is there can be 2 electrons in every orbital, but they need to have opposite spins. So while one has a spin upwards, the other one will have a spin downwards. And notice this is a half arrow. If you want to draw a whole arrow, that's totally fine. Okay? For 2s, again, you only have 1 orbital, 1 large sphere. And you have 2 electrons in there, so it's going to be 1 up, 1 down. For 2p, remember there are 3 different orbitals, 3 different shapes along the x, the y, and the z axis. So I'm going to have 3 boxes to represent my 3 orbitals in the p sublevel. Okay? There's one more rule I have to explain, and that is this. When you're filling orbitals, you first fill orbitals, each orbital with 1 electron with a specific spin, and then you can go back and continue filling orbitals. So this is what it looks like. I can fit a total of 6 electrons in the 2p sublevel. So 1 electron, 2 electrons, 3 electrons, go back, 4 electrons, 5 electrons, 6 electrons. Okay? In 3s, in that sublevel, I have 1 orbital and 2 electrons. 1 up, 1 down. For 3p, remember p has 3 orbitals. 1, 2, 3. Okay, I'm going to go up, up, up. That's 3 electrons. Down, down. That's a total of 5. So this, if I ask for the orbital diagram, is what I'm asking for, not this. Because while this is manageable with chlorine, as soon as I get larger, like when I talk about iron in a second, it's going to get really messy. And you'd have to draw your d orbitals, which gets even crazier. All right, let's look at iron. All right, for iron, the electron configuration is the following. 1s2, okay, so let's draw out the orbital diagram. So 1s has 1 orbital with 2 electrons, 1 up, 1 down. 2s has one orbital, one up, one down. 2p has 3 orbitals. One up, one up, one up, one down, one down, one down. 3s has 1 orbital. Remember, s has 1 orbital. Here I'm going to create a quick cheat for you. The s sublevel has 1 orbital. P always has 3. And D always has 5. And while we will not be drawing them, if you notice 1, 3, 5, F therefore has 7. And remember, each orbital can fit a total of 2 electrons in them. Okay? For 3p, 3 orbitals, 1, 2, 3, 4, 5, 6. For s has 2, 1, 2 electrons in 1 orbital. And then for D, I've got to drop 5 orbitals. 1, 2, 3, 4, 5. So I'm going to fill it 1, 2, 3, 4, 5, 6. So much more manageable than the monstrosity that I created up above. That is your orbital diagram. Okay, let's look at one last one. All right, for vanadium. There's my electron configuration for vanadium. Okay. I'm going to draw my orbital diagrams. 1s has 1 orbital with 2 electrons. 2s has 1 orbital with 2 electrons. 2p has 3 orbitals. 1, 2, 3, 4, 5, 6 electrons. 3s has 2 electrons. 1, 2. 3p has 6. 1, 2, 3, 4, 5, 6. 4s has 1 orbital. 1, 2. And for the last one, a lot of students say, well, if I only have 3 electrons, do I have to draw 5 orbitals? And the answer is yes. And the reason why is these electrons, even though you're going to have empty orbitals, you need to show that they are still present because electrons can actually jump between orbitals. So this electron could technically jump into that orbital. So by not drawing it, you're not acknowledging that it exists. And you're making it seem like you're talking about the p sublevel and not the d sublevel.